Hi Statistics, Miss Hurley here. I am going to start today by going over the exit ticket from yesterday, and then we'll move forward with today's notes. Okay, you've already read this, but again, we're working with our two Darby teachers. They take a random sample of 100 students from their classes and record the proportion of students that did their homework last night. When they're finished, Trevor finds that 60% of the students he surveyed had done their homework, and Nick finds that 68% of the students he surveyed did their homework. The difference in their proportions was 0.08. Our first job is to calculate a 68% confidence interval for the difference in the proportion of Nick's students who complete their homework and Trevor's students who complete their homework. So a confidence interval starts with that difference, Pn minus Pt. So we would say 0.08 plus or minus. Now we're doing a 98% confidence interval. So what that means is we have these areas to the left and the right, and in between we have 98%. So here we have 1% and 1%, and when we move that decimal, that's actually 0.01. And so inverse norm would be 0.01, 0, and 1. Okay, when we do that in our calculator, we get, .0101, negative 2.33, so plus or minus 2.33. And so that goes here. And then we have our square root. And we use 0.68, 1 minus 0.68 over 101, and then 0.6 also over 100. Now we did that piece of the equation up here in our notes, didn't we? I think we did it. Oh, you did it yesterday in your exit ticket maybe. Yeah, right here, 0.07. Okay, so I'm not going to plug that all in. I just know it's 0.07. So I have 0.08 plus or minus 2.33 times 0.07. And so I'm going to multiply that 2.33 times 0.07, and I get 0.16 as my margin of error. So when I subtract that, I get the lower value of my interval, which is negative 8%. And when I add it, I get positive 24%. Okay, now the next part, or the next thing we need to do, is calculate the test statistic for our test of significance. And this was not something I did for you yesterday in the notes. This was something you were doing on your own, just to see how you did. And that test statistic is Z. Okay, on the top, or in the numerator, we do that difference in percent, so 0.08, P1 minus P2, minus 0, over the square root, and this is where we need that PC. So what we can do, typically that PC is the count of all successes over the total number of individuals. Now here we have our 2%, but we also know that those are percents of people out of 100. And so what we can do is we can say Trevor found 60 students out of his 100 and Nick found 68 students. So PC, or that combined percent, would be the 60 plus 68 over 100 plus 100. And remember, it's only 60 and 68 because it was out of 100 students. So those percents translate easily. So 68 plus 60 is 128 over 200 is 64%. So then when we do this denominator for our test statistic, we would say 0.64 times 1 minus 0.64 over 100. And then we actually repeat that. That only works that we repeat it because our sample size is the same in both of our samples. So 0.64 over 100. So 0.08 goes on the top, over top of, now I'm going to do in my calculator, 0.64 times 1 minus 0.64 over 100. I get 0.002. So that's 0.004, and I'm taking the square root of that 0.004 is 0.06. I get 1.33 as my test statistic there. Okay. Now here we're doing a full example. It says researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. And at school 2, a simple random sample of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? Carry out a significance test at a 0.05 level to support your answer. So our parameter right away is going to include 2 important things. The very first word is going to be difference. And that's because our sample number, our sample statistic, is a difference in the percents of students who don't eat breakfast. So the keywords there are difference and percents. So we know we've got 2 percents and that they are percents, not just a number of or something like that. Now remember, your null and your alternative hypotheses always start with P1 minus P2. And that null, more specifically, always says that that difference is 0, assuming that those percents are the same for both schools. Now what this says is, do these data give convincing evidence of a difference? And a difference would be noted not if one was big, if it was greater than or less than 0, but just not equal to 0. Right? If it said, does this give evidence that school 1 has a higher percentage, that would be greater than 0. If it was school 2 has the higher percentage, then it'd be less than 0, because if we subtracted a small number minus a big number, we get a negative number. This is 0.05. Then our conditions. We're still working with a random, independent, and normal. Okay, it's a simple random sample. And then for normal, we need our percents. So we know our first school had 80 students, but we need to find P hat 1 and P hat 2. Right, in school 1 we had 80 students and 19 of them had not eaten breakfast. And at school 2, 26 of the 150 had not. So when I plug those in, 19 over 80 is 0.24. And 26 over 150 is 0.17. So 80 times 0.24 and 80 times 1 minus 0.24. Then 150 times 0.17, 1 minus 0.17. So this would be 19 and 61, 26 and 124. Okay, all greater than or equal to 10. So it is normal. Then our test statistic Z, this is what we just did. So the first thing you do is you take the difference in your percents, P1 minus P2. and you subtract that assumed value for your difference, which is always 0. So this thing right here, this minus 0, that's really optional. It's not going to change anything. So you might at some point see me not write it. That would just be because it's always minus 0, so it doesn't impact it. Then we have to find our PC. And so we're going to take the count of successes. So in school 1, that was 19, school 2, 26. Over the 80 plus 150. Okay, so 19 and 26 is 45. And 80 plus 150 is 230. 45 over 230 is 0.20, 0.195 to be specific, but then when you round. So down here we have our square root. And we do it over each of our separate n values. Okay, 0.24 minus 0.17 is 0.07. So then I plug this in, and remember I do not do it all at once. So 0.2 times 1 minus 0.2 over 80 is 0.002. And 0.2 times 1 minus 0.2 over 150 is 0.001. So now I'm square rooting 0.003, which is 0.05. 0.07 divided by 0.05 is 1.4. So that's my test statistic. Now remember, this was not equal to, so I'm going to be centered at 0, but have negative 1.4 and positive 1.4. And I'm going to look at this area to the left and this area to the right. And when I find that p-value, I'll do normal CDF. I always do that lower percent. And that is 0.08. Now I multiply that by 2, and I get 0.16 overall. So then I compare that to my level of significance. 0.16 is greater, so we fail to reject. Okay, so really, guys, the big thing that's different for these tests of significance are these hypotheses, right? Just remember it's P1 minus P2 equals 0, always, always, always for the null. And then not equal if we're just seeing if there's a difference, greater than if P1 is greater, less than if P1 is less. All 0 though. We have to check for both being normal, and then that PC part comes in for our test statistic. Okay, let me know if you have questions or you need clarification. Here's your exit ticket. You're running another test of significance, and I will give you feedback on that tomorrow. Okay, hope you have a great day. It's Wednesday. We made it halfway. Woohoo! Talk to you guys soon.